Everyone, this Infinity YouTube channel. Please remember to like, subscribe, and share. Alright, today we are going to go through a topic called the Laplace transform. So this Laplace transform is actually a function, is an integral that helps us to transform functions from the t space to the s space. So as we go further, I will explain what the t space means and of course what the s space means. So this Laplace transform as well helps us to solve equations like the differential equations. So it helps us to reduce the ambiguity of solving ordinary differential equations. So we are going to solve some certain functions on this Laplace transform, and we are going to see how these functions helps us to analyze ordinary differential equations. So the Laplace transform is given by Laplace is written as this form, Laplace of f of t. Laplace of f of t is given by the integral of 0 to infinity exponential of minus st f of t dt. Alright, this is the definition of the Laplace transform, where as you can see the Laplace of f of t, and as you can see that the f of t reflected inside of the integral. So that is to tell you that we are going to transform all the functions from the t word to a certain function in the s direction, in the s word, in the t space. Right, so for us to understand this Laplace transform, we are going to understand some certain functions on how those functions work while solving the Laplace transform. So the first one we are going to study is the Laplace of a constant, right? The Laplace of a constant. So let's assume that f of t is equal to a, and let that a be a constant. So let's pick a as a constant. You can decide to pick any other letter, any other alphabet as a constant. But for the sake of this video, let us assume that a is equal to that certain constant. Now we are going to find the Laplace of this a. So if a is same as f of t, then wherever we see f of t, we are going to use a to represent the f of t. Hence the Laplace of a. Hence, the Laplace of a is equal to the integral from 0 to infinity exponential of minus st. The only thing I'm changing is the f of t. St a dt. Right? So this is the definition of the Laplace of a constant. Now, when you have this type of integral, so we are going to integrate these functions. So what are we going to do? What should we do? So one of the ideas of integrals is that a constant can come out of the integral. Okay, that's one of the basic rules of integration. So if the constant a comes out of this integral, we will have a integral of 0 to infinity exponential of minus st dt. Alright, so this is what we are left with. So from here now, we can integrate further. So the only thing we are going to integrate from here is this function, right? So if you can integrate the exponential of minus st, then we have been able to decipher this integral. So let's integrate this. Now if you want to integrate this, it's a basic integral, the exponential of minus st. So if you integrate the exponential of minus st, the answer you are going to get is exponential of minus st divided by s. Of course, there is a minus outside the integral, the answer, okay? So you are going to have this as your answer. But remember that a multiplied the entire function. So we are going to use a as well to multiply this entire function. So this is the value of the integral after we dissolve it. So but remember that the limit of this integral is from 0 to infinity. infinity, right? So we are going to extend this integral from 0 to infinity, and we are going to plug in the values of these functions into what we integrated. Hence, if you should do that successfully, we are going to have, if you plug in infinity into here, we are going to subtract the upper limit from the lower limit, okay? So when we plug in infinity into this, we are going to have a into minus exponent of minus s, because the values of this upper and the lower limit are the values of your t. Are you there? So you are going to impute this upper and the lower limits into the values of your t. So that means instead of me writing t, I will replace it with infinity divided by x. Alright? Okay. So minus, there's a minus here already, so it's going to turn to a plus. Okay? Exponential of minus s into 0 divided by x. So this is the value of this function. Now, I want you to note that the exponential of a negative infinity should give you 0. And the exponential of 0 should give you 1. That is to tell you that this is now equal to a into minus exponential of, if s multiplies infinity, right? If s multiplies infinity, you are going to have infinity. So, and of course, there's a negative outside this function. So it's going to be negative infinity divided by x plus, if s multiplies 0, of course, it's going to turn to 0. So what you are going to have is negative exponential of 0 into x. So of course, as usual, this turns to 0 because the exponential of minus infinity is going to give you 0. So what you are left with is only exponential of 0, which is of course is 1. So that means the answer to this integral is a into 1 over x, which is equal to a over x. That means the value of the Laplace of a constant a is going to give us a over x in the integral function. Example, let's assume that we are asked to solve for the Laplace of 2. It asks to solve for the Laplace of 2. Mind you that this answer to this integral can only be valid if s is greater than 0. Alright? So you must exemplify this by saying that a over x is the answer to this integral on the occasion that, on the condition that s is greater than 0. Alright, so let's continue now. If we are asked to solve for the Laplace of 2, now the Laplace of 2 here, 2 is a, so that means the answer becomes 2 over x as the final answer. Let's take another example. Let's say Laplace of minus 7 over 3. So Laplace of minus 7 over 3 is same as saying minus 7 over 3x. So this is just a few example on how to understand the Laplace of a constant. Alright, so that is that for a constant. Now let's go through another function that is not a constant. Right? Let's go to another function. Alright, so let's assume in this situation that f of t is now equal to the exponential of at. F of t is equal to the exponential of at. Okay? So what it means is that we are going to find the Laplace of the exponential of at. And of course, the Laplace of exponential of at is equal to the integral of 0 to infinity exponential of minus st exponential of at dt. Alright, so this is the value of, this is the definition of the Laplace 80. Alright, so the idea now becomes, how are we going to integrate this kind of function? How can we decipher this function? So, but mind you, that the exponent here, they are the same, right? So using the law of indices, we can decide to add their powers, because this is actually a multiplication. So we can decide to add their powers. So if we should add the powers using the law of indices, this becomes the integral from 0 to infinity exponential of minus st plus 80 dt. Right? So this is what we are going to have. Now from here now, we can decide to factor out c. Okay? We can decide to factor out c to simplify this our function. Now if you factor out c, you are going to have the integral from 0 to infinity exponential of minus t into s minus a. Alright, so that's what we are going to have. So if you factor out t, this is what we are going to have. Right? So the only thing I decided to do here was to factor out minus t outside. And of course, if you factor out minus t outside, minus t times s gives you minus s. Minus t times minus a gives you a positive 80. So this is what we have. Now let us integrate this function. So just like the original one that we did earlier on, the integral of an exponent is actually easier. So but let me give you a step-by-step procedure on how to integrate this kind of function without knowing the original integral. So when you have something like this, so what you should do is that, because we know the from our standard integral, we know that the integral of exponential of x is equals to exponential of x. So on that note, let us change this function to represent this type of function, right? So on doing that, what we have there is, we can say let u equals minus t s minus a. So if we let t equals the power of this exponential, we can be able to make it to resemble this type of integral. So if you should do that, but remember that if we should let u to be equal to the power of this exponent, that means we are going to change this dt to du, right? So the only relationship that can make us change dt to du is by differentiating this term. So if you differentiate this term, you are going to have du is equals to, and differentiating u will just get to c. So what we are going to have left is minus s minus a dt, right? If you should differentiate, this is what you are going to have. So from here now, we need to get the value of dt in terms of du. So dt now is equal to du divided by minus s minus a. So this is what we are going to have. Now, since we've got to this, let us write this integral. So this integral from here now is equal to the integral. Let's assume that this integral is still under the same limit. So it's from the integral of 0 to infinity, exponent of, instead of writing minus t s minus a, we are going to write just u. And instead of writing the t, we are going to write du over minus s minus a. So this is what we are going to have. And of course, we can take this outside of the integral because we are now dealing with u. That means s and a are now constant. So if you should take this outside of the integral, this becomes minus 1 over s minus a, integral of 0 to infinity, exponential of u du. And of course, as you can see from here, it resembles this integral. Hence, this is equal to minus 1 over s minus a into the exponential of u. And of course, we know that this u is same thing as saying minus t s minus a. So that is to say, this is equal to minus 1 over s minus a into exponential of minus t into s minus a. So this is what we have as the answer. But recall that the limit is from 0 to infinity. So since the limit is from 0 to infinity, we are going to impute it into this function. So let's just finish it up here. So when I impute, remember that I told you that infinity is the value of your t. Are you there? Infinity is the value of your t. So if you impute infinity into this integral, it becomes, if you impute infinity into this integral, it becomes minus 1 over s minus a into the exponential of minus infinity into s minus a. Okay? Then minus exponential of minus 0 into s minus a. Alright, so this is what we have. So from here now, we know that minus infinity, of course, is going to give us 0 from what I've written in the previous example. So that means this gives us 0, and then this gives us 1. Okay, this gives us 1. So of course we have a minus 1 here. So when minus multiplies the minus 1, we are going to have 1 over s minus a as the value of this function. So that is to tell you that the Laplace of exponential of at is equals to 1 over s minus a. Example. So let's say you were asked to find the Laplace of 2t, the Laplace of exponential of 2t. Let's say you have to find this Laplace. Just impute that the Laplace is equals to 1 over s minus 2. Just change, since 2 here is same thing as a, just change the value from there. Alright, so let's say we have to find the Laplace of exponential of minus 2t. So in this situation now, the minus will affect this, that is to say it becomes 1 over s plus 2. So this is how to analyze the Laplace of a function of an exponent. So we are going to go through the third one, and then we are going to see how we can analyze this function. So that's it. Alright, so we are going to continue from the Laplace of when f of t is equals to t raised to the power of n. So we've done the Laplace of the exponential of at, we've done the Laplace of a constant. So this is the third one we are going to do. So, but this particular one, I feel is one of the most complex parts of the Laplace. So I'm going to use 3 methods. I'm going to approach this in 3 methods. So whichever one that is more convenient for you, then you can use it, okay? But I will try as much as possible to make the 3 methods easy to understand, to comprehend. So in your exams or in your day-to-day reading, any of the methods is correct. So whichever one that you choose to do, you can go ahead to do it. Alright, so for the first method, method 1. So remember that if I ask you to find the Laplace of t raised to the power of n, if I ask you to find the Laplace of t raised to the power of n, what you say is it is equal to the integral of 0 to infinity exponential of minus st t raised to the power of n dt. So this is the usual, this is the definition of the Laplace of t raised to the power of n. Are you there? So now let's continue. So since this is equal to this, so and if I look at this integral, so it actually looks like a gamma function integral. It looks like a gamma function integral, and the gamma function says that gamma of n plus 1 is equal to the integral from 0 to infinity exponential of minus t raised to the power of n dt. So, alright, so this is the definition of the gamma of a function. This is the definition. So, let's continue. Now, and this definition is actually equal to n factorial. This definition is equal to n factorial. So, if I try to make this function to look like this, it will help me analyze and get the value of this integral very comfortably without solving lots of functions. So what I have to do is just to make this integral to look like this. Are you there? So what we are going to do is, for us to make this integral look like this, the only thing we have to do is we have to make the power of this exponent the same as the power of this exponent. So if from here now, if I say let u equals st, okay? If u is equals to st, it doesn't matter the letter that I'm using, okay? The only thing that matters is for me to make these integrals to be the same, to resemble each other. Alright, so if u is equals to st, I'm trying to change from c word to my u word. So if u is equals to st, then it means that t is equal to u over s. Are you there? So since I'm trying to change from u to s, I have to differentiate both sides. That means du is equals to s dt, which means that dt is equals to du over s. So this is me trying to make these integrals to be the same. So the next I'm going to do is to impute whichever function that I have here into this integral. So if I should impute that, what I'm going to have is the Laplace of t raised to the power of n is equal to the integral from 0 to infinity exponential of, so instead of writing minus st, I'm only going to write minus u. So exponent of minus u. Now, instead of writing t is equals to u over s, right? So since t is equals to u over s, that means u over s, which is t. And remember that t was raised to the power of n. That means raised to the power of n. Okay? And the t here is same as du over ds. That is to say, the t is now du over s, as you can see. Alright, so the next thing we are going to do is to break down this integral. So this integral, of course, is equal to the integral of 0 to infinity exponential of minus u. Using the law of indices, I can decide to break this down. So if I should break this down, this is equal to u raised to the power of n divided by s raised to the power of n multiplied by du divided by s. So since this and this are the same, I can decide to add their powers on the value of my s. So this is not the same thing as saying integral from 0 to infinity exponential of minus u raised to the power of n divided by s raised to the power of n plus 1 du. Are you there? So since I have this, I can decide to extend my s out of the integral, because in this situation, s is now the constant. S is now a constant in this integral. So since s is now a constant in this integral, this is now equal to 1 over s to the power of n plus 1, the integral of 0 to infinity exponential of minus u raised to the power of n du. So this is what I have, right? So now let's compare this and this together. As you can see, of course, the integral is from 0 to infinity. The integral is from 0 to infinity. Exponential of minus t, exponential of minus u is just the letter, so they are the same. Then t raised to the power of n, u raised to the power of n is still the same. That is to say, this is actually, this integral this integral is actually equal to gamma of n plus 1. Okay, this is written as gamma of n plus 1, which is equal to n factorial. So since this integral is equal to n factorial, remember that 1 over s raised to the power of n minus 1 was outside of the integral. Hence, this is now equal to n factorial divided by s to the power of n plus 1. That is the value of your Laplace of t raised to the power of n. So this is the value. Now, example, if we are asked to find the Laplace of t raised to the power of 3, so this is basically equal to 3 factorial divided by s to the power of 3 plus 1, which is equal to 6 divided by s to the power of 4. If we're asked to find the Laplace of t raised to the power of 2, so this is basically equal to 2 factorial divided by s to the power of 2 plus 1, which is equal to 2 over s to the power of 3. So this is how to analyze the Laplace of t raised to the power of n. So basically this is the first method. So we are going to go through the second method and we see which one that is more easier to use. So alright, so let's continue from what we stopped. So we are going to do the second part, the method 2 of solving these Laplace. So I might decide not to. We know the original definition of Laplace of t of n as the Laplace of t of n. We know that Laplace of t of n is equal to the integral from 0 to infinity, exponential of minus st, t raised to the power of n dt. So but I might decide not to use this definition, but I'll still arrive at my answer. Right? That's the second method I'm going to teach you. So what we are going to do is we are going to use our knowledge of the Laplace. We are going to use the knowledge of the Laplace of exponential of at. Okay, we'll be needing this idea. So recall that we've already done the Laplace of exponential of at, and the Laplace of exponential of at is equal to 1 divided by s minus a. So as long as s is greater than a and of course it's greater than 0. So this is the definition of the Laplace of exponential of at, right? So since we have this, the next thing we are going to do is we are going to borrow a little knowledge from the series integral, series functions. So this idea, this method 2 that I'm solving now is gotten from the idea of the Taylor and the Maclaurin series, right? So I've done a video on the Taylor and Maclaurin series, so you can go and watch the video. So but this idea was also from there. So from the Taylor and Maclaurin series, we know that the exponential of x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot dot dot, right? So this is the representation of the exponential of x. So and this exponential is equal to the summation of n equal to 0 to infinity x raised to the power of n divided by n factorial. So this is the value of the exponential of x, right, from the Taylor-Maclaurin series. So using that same knowledge, I want to represent the exponential of at in form of the Maclaurin series. Okay, so the exponent of at here, if I should link it with the exponential of x, is equal to the summation of n equals 0 to infinity. So here, x is now replaced with 80. So whenever I see x, I'm going to use 80 to represent x. Hence, this is going to give me 80 raised to the power of n divided by n factorial. Right? So this value of the Laplace I'm going to have, the value of the function I'm going to have. So this I can decide to separate this using the law of indices. So if I should separate this using the law of indices, this is equal to the summation of n equals 0 to infinity a raised to the power of n over n factorial multiplied by t raised to the power of n. Right? If I should use law of indices to separate these. So this is what we have as the value of the exponential of at. Now, as well, we are going to borrow a little knowledge from our Taylor-Maclaurin series as well. So from the Taylor-Maclaurin series, we know that 1 over 1 minus x is equals to the summation of x raised to the power of n from n equals 0 to infinity. So as long as x is greater than 0, right? As far as x is less than 0, rather, as far as x is less than 0. Okay, so this is the idea of the Taylor-Maclaurin series. So if you should have something like this, the next you are going to do is, we know that the Laplace of exponential of at is equals to 1 over s minus a. So since the Laplace of exponential of at is equals to 1 over s minus a, let us rewrite this as this. Okay, so 1 over s minus a can be rewritten as, I want to write this as this, okay? So of course I have 1. So the only thing I need to change here is this x. So how can I change this x? So for me to change this, I'm going to have 1 over a into 1 over s into 1 minus a over x. So this is what I'm going to have. Of course, if you should multiply this, you are going to have this function back. Because 1 over s times 1 gives you s, and s times 3 over s gives you a. So this is what we are going to have. So since I have written this as this, I want to write this function as this one. Right? So if I should write this function as this one, it will help me get the answer that I am working towards. Hence, this is now equal to the summation of n equals 0 to infinity, right? Now recall that I want you to note that in this situation 1 over 1 minus a over s is just this, but 1 over s is outside of this function. Hence, what I'm going to have is a over s raised to the power of n. But remember that 1 over s is outside, so you can just put 1 over s outside. Let's go again. I've actually represented this function as this, okay, by just factorizing. I just factored out s and made it to look like this. So using this particular function, when we have 1 over 1 minus x, the only answer to the series will give you only this function raised to the power of n. The same idea when you have, let's assume that this s was not here, right? Let's compare these two. Let's assume that the s was not here. Let's compare these two. So since if you have this and x will only take the value of the n, the same way if you have this, a over x will take the value of the n. But the difference between this and this is that in this situation, x was present, right? The s was 1 over x. That is why I have this 1 over x outside of this function. Now, I can decide to break this down further by saying 1 over x into the summation of from n equals 0 to infinity, a raised to the power of n divided by s raised to the power of n. So this is the definition of this. Now, I've brought out all my factors. Now let us do a little comparison and see how we can solve this. Remember, the whole idea that we're using so far was gotten from the Laplace of the exponential of at, right? Good. So since the Laplace of the exponential of at is equals to 1 over s minus a, so Laplace of the exponential of at, and we know that exponential of at is equal to this, right? That is to say, instead of writing Laplace of exponential of at, I will write the Laplace of the summation of from n equals 0 to infinity, a raised to the power of n divided by n factorial, c raised to the power of n. Right? Then we know that this Laplace is actually equal to 1 over s minus a, right? That is to say, 1 over s minus a was rewritten as 1 over s multiplied by this sum. Hence, this Laplace is equal to 1 over s summation of from n equals 0 to infinity a raised to the power of n divided by x raised to the power of n. Alright, so this is what we have. So I can decide to bring this s outside. It doesn't affect my function. And I can decide to bring summation of n equals 0 to infinity a raised to the power of n multiplied by n factorial outside of this Laplace. It doesn't still affect my function. So if I should do that, what I'm going to have is the summation from n equals 0 to infinity a raised to the power of n divided by n factorial into the Laplace of t raised to the power of n. Recall that all these have been doing so far was just to get the Laplace of t raised to the power of n, and then this idea helped me to arrive to achieve my aim. Now, since this is same as this, I just took out the summation outside of the Laplace. The same way I can decide to take 1 over x, x raised to the power of n outside, right? So if I should do that, of course I'm going to have 1 over, since s and s are the same, we can add their powers. So when I add their powers, I'm going to have x raised to the power of n plus 1, summation of from n equals 0 to infinity. So this is basically what I have, a raised to the power of n. Now let's do a little cancellation. So this particular function I wrote on my left-hand side, I can decide to rewrite this one on my left-hand side as 1 over n factorial, summation of from n equals 0 to infinity, a raised to the power of n, Laplace of t raised to the power of n. And of course, on my right-hand side, I have 1 over x raised to the power of n plus 1, summation of from n equals 0 to infinity, a raised to the power of n. So this is why I'm doing all this, is to have a very easy cancellation. So from here, I can cancel these and these because they are the same, right? So the only thing I have left is 1 over n factorial, Laplace of t raised to the power of n is equal to 1 over sn plus 1. So I can decide to multiply both sides by, let me fix it here, okay? So I can decide to multiply both sides by n factorial. So if I should multiply both sides by n factorial, I'm going to have n factorial multiplied by 1 over n factorial, the Laplace of t raised to the power of n is equals to the n factorial multiplied by 1 over s raised to the power of n plus 1. Hence, if this becomes the case, n factorial cancels n factorial, that means the Laplace of t raised to the power of n is equals to n factorial multiplied by 1 over s raised to the power of n plus 1, and of course this is going to give me n factorial divided by s to the n plus 1. So this is the second method on how to solve the Laplace of t raised to the power of n. So this looks a bit ambiguous, but I hope this is also very useful and helpful. So we are going to go through one more example. Recall what I told you earlier on, that I'm going to use up to 3 example methods to do it. So whichever one that's easy for you to comprehend, whichever one that's easy for you to understand, you can go ahead to use that one. So let's go through this third method and let's see how it's going to turn out. So alright, let's go through the third method of solving this Laplace of t raised to the power of n. Alright, so let's go. So when you have we know as usual that this is the definition of the Laplace of t raised to the power of n, right? This is the definition. So, but when we look at this, it reminds us of integration by parts, right? Because these two functions are actually a product. They are multiplying themselves, hence we can use integration by parts. So let's go through integration by parts to do this. So for the sake of this video, we are going to call integration by parts as IBP, integration by parts, to shorten it. Okay, so we are going to use IBP to integration by parts to do this function. Now, using integration by parts, there is a short code that we use to integrate by parts successfully and easily. So that code is called light. You can call it light. Okay? So some textbooks might use irate, some textbooks might use light, but for me, I think I'll go with this. Alright, so this light, L means logarithm. I means inverse three functions. A means algebra. T means trigonometric functions, and of course E means exponents. Exponentials. So what this basically means is that when you want to solve the integration by parts, we know, I'm going to show you how to use this. We know that integration by parts is equal to uv minus integral of v du. This is the definition of integration by parts. That is, the integral of u dv is equal to this. So this is the definition of integration by parts, okay, called IBP. So now what this means is that looking at this formula that I have on the board, you will see that we need the value of our u, we need the value of our v. So the IBP helps us to know which function is going to come first when we are trying to use the value of our u. Only on u, okay? The IBP helps us to know which one we are going to use as our u. That is to say, when you are dealing with a function on integration by parts, you are going to look out for, because the function has a logarithm. If the function has a logarithm, that means logarithm will take the value of your u. So, but if the function doesn't have a logarithm, look at the function. Does it have an inverse trig function, inverse trig identity? If it has, like arctan, arc cos, arc sine, that is tan inverse and sine inverse. If it has, then that will be the value of your u. Now, the next is, if it doesn't have an inverse trig function, does it have an algebra? If it has, like x, y, and so, then you check out if it has a trigonometric identity, like sine, the cosine, and the tangent. So if it doesn't have, then check out if it has an exponent. This is just a hierarchy of how to use your u. This should be a hierarchy, okay? So L comes before I, before A, before T, and before E. Then, when you have used any of them as your u, the next one should be the value of your dv. Are you getting that? Should be the value of your dv. So let's go. So, now looking at this function now, I have an exponent and I have an algebra, because T, of course, here can be called an algebraic expression. So, algebra and exponent, which one comes first? As you can see, algebra comes first. Hence, algebra is going to take the value of our u. So hence, u now is equals to t raised to the power of n. And we are going to differentiate it. So the u is equals to, using the basic rule of differentiation, this is going to give me n t raised to the power of n minus 1. And then the next is going to be the v. The v, since I've used u as the value of t raised to the power of n, the v is going to be exponential of minus st dt. Alright? The remaining part of the integral. So for me to get the value of this, for me to get the value of v from here, I have to integrate both sides. So if I should integrate both sides, v is equals to minus exponential of minus st divided by x. Alright, so we are going to plug in this value into this formula of integration by parts that I wrote at the board. So let's go. So u, which is t raised to the power of n, multiplied by v, which is minus exponential of minus st divided by x, minus the integral of v. What is the value of our v? Minus exponential of minus st divided by x, multiplied by our du. What is the value of our du? Du was equals to this. So du was equals to this. That means we have multiplied by n t raised to the power of n minus 1 dt. So this is what we have as the value of this integral. So since this one is already here, let's hold it. So now let's continue. But as you can see, I have from here now, I have another integral inside this function again. That is to say, we are going to use integration by parts again. But mind you, in an integral, you can use integration by parts twice, thrice, as many times as you can, just to integrate a function. Right? It's not just limited to using it once. So, but we have to know that this integral, recall, is from 0 to infinity. Alright, this is from 0 to infinity. So let's continue. Now, if I should put the value of infinity into this c and 0 into this, what I'm going to have is minus infinity raised to the power of n exponential of minus s into infinity divided by s, right? Minus 0, I'm now inputting 0 now, minus 0 raised to the power of n exponential of minus s into 0 divided by s as well. Now, minus times minus gives me a positive, plus integral from 0 to infinity of exponential of minus st divided by s multiplied by n c raised to the power of n minus 1 dt. Alright, so this is what we are going to have. Okay, so if you should do that now, we are going to have, I know that minus infinity minus s times infinity gives me minus infinity. And minus infinity, expression of a minus infinity is going to give me 0. So this goes to 0 plus, now since 0 of course is multiplying every other stuff here, that means this integral as well goes to 0. So the only thing I have left is this integral. So let's break this further. So this is equal to, I can decide to bring n and s outside of this integral. If I try to bring n and s outside of this integral, this is going to give me n over s integral of 0 to infinity exponential of minus st t raised to the power of n minus 1 dt. That is to say, the Laplace of t raised to the power of n is equals to, the Laplace of t raised to the power of n is equals to this. Alright, so what we are going to do again is that we are going to use integration by parts again to differentiate this and to integrate it. So that is to say, u now again is equal to t raised to the power of n minus 1, and the u is equal to n minus 1 t raised to the power of n minus 2 dt, right? So this value for u, and of course the v as usual is equal to exponential of minus st dt. So since I've done it here already, that is v is equal to minus s exponential of minus st divided by s. So this is the value of our v and the value of our u. So we are going to plug it in back into this integral. So this is equal to n over s into, remember that this integral is done using integration by parts, right? And this is the formula for integration by parts. So we are going to use that same formula of integration by parts in this bracket. So u here now is t raised to the power of n minus 1. So this is t raised to the power of n minus 1. And v here now is minus exponential of minus st divided by s, right? So this is what we have. Minus the integral of u of v du. So minus the integral of v du. So this, since there is minus on this v, let me just change it to positive. So I have minus exponential of minus st divided by s multiplied by our du. And the value of our du is n minus 1 t raised to the power of n. Okay, value of our du here is t raised to the power of n minus 2 dt. So this is what we have, right? So let's expand this bracket. Let's expand it. So this is equal to n minus n multiplied everything. I have minus n t raised to the power n minus 1 exponential of minus st divided by s times s gives me s squared plus n over s plus n over s integral of 0 to infinity exponential of minus st Explanation of minus st n minus 1 t raised to the power of n minus 2 dt. So this is what we have if I should expand these brackets, right? So I have s here. So this is what I have if I should expand these brackets. Alright, so now let's plug in the value of our limit again on this function from 0 to infinity. Remember that whenever you are done with your uv, anytime you are done with your uv, the next you should do is to plug in the value of the limits that you were given in the equation. So that will help you to simplify the function. So from here now, I know that if I should put infinity again into this function, I'm going to have 0. If I should put 0 into t, I'm going to have 0. That means this entire equation comes to 0. Now let's go back to the second one. So what I have left is equal to n over s multiplied by, I can decide to bring out n minus 1 over s outside. So if I should bring out n minus 1 over s outside, I'm going to have n minus 1 over s into the integral of 0 to infinity explanation of minus st t raised to the power of n minus 2 dt. So this is what I'm going to have. Alright, so we are going to do, as you can see again, we have another integration by part. I'm going to do it one more time, then I will show you something, right? We're going to do it one more time. So, looking at this now, you can see that the t on the value of your t is actually increasing. Initially, t was just only t to the power of n. Then when I integrated, it went to t n minus 1. When I integrated again, it went to n minus 2. That is to tell you that if I should integrate again, I'm going to have the same ideology. I'm going to have something like n over s multiplied by n minus 1 over s multiplied by n minus 2 over s into the integral of 0 to infinity expression of minus st t raised to the power of n minus 3 dt. Right? If I should integrate again, this is what I'm going to have. And if I should integrate again, n minus 2 will come out, it will turn to n minus 4. It will keep on increasing. So having this idea at the back of our mind, let us just create a recursive formula for this. Let's create a recursive formula. So creating that recursive formula now. Okay. So creating that recursive formula here. Okay, now creating a recursive formula here, we can see that n is increasing by n minus 1, n minus 2. So let's get that. So on the numerator, I'm having n into n minus 1, n minus 2, and n minus 3 till infinity divided by, and my s is actually increasing by, okay, this should give me, okay, sorry. If I should expand this, I'm going to have x squared, right? So this should give me, and the s on this other one is increasing by 1. The s is increasing by 1. This should be s squared, okay? And this should be s cubed. It should be increasing by 1. The s will be increasing by 1. So having that at the back of our mind, so this is going to, that shows that the n is increasing by n plus 1, right? While the n raised to the power of n minus 1 is increasing by minus 1, minus 2, minus 3. So if you have this as the numerator, this simply means n factorial, because n factorial means n into n minus 1, minus 2, minus 3 till infinity. And since the denominator is increasing by 1, that is to say the denominator will just be s to the power of n plus 1. Alright, so I hope you understand what I mean. So since the numerator, the denominator is increasing by one step at a time. Are you saying me? When I did initially, I had only one s. If I integrate again, I had another s. If I integrate it again, I have another s. That is to say the s was increasing one after the other. Okay, from 1s to 2s to 3s to 4s. Yes, we are increasing. Hence, we can create that this is equal to n factorial divided by s is equal to n plus 1. So I feel these are also very comprehensible. So we are going to go through another f of t. This is all I have to do on t raised to the power of n. So we are going to go through another f of t. We're going to see how we can integrate such function. We're going to go through another f of t, right? We've done the Laplace of a constant, the Laplace of an exponent, the Laplace of the series to the power of n. So we're going to go through another Laplace. That is the Laplace of when f of t is equal to either cos bt or sin bt. Okay, either the cosine of bt or the cosine of or the sine of bt. So it depends on the textbook you are using. Some textbook might use A as A instead of B, but it doesn't matter, right? So either you use A or you use B. Okay, so let's go through this. Now this other one as well is this other one as well, you can use very two methods to approach it. So we are going to see how we can use these two methods to approach it. So whichever one that is also easy for you to comprehend, you go with that. Now the first method I'm going to use is actually going to be quite simple. So the first method is we are going to employ the knowledge of our Euler theorem, Euler's law. So from our Euler's law, it states that the exponential of I theta is equals to cosine theta plus I sine theta, right? So this is from our Euler's law. This is what it says. Euler. From our Euler's law, this is what it states, right? So now we are going to also use the idea of our the Laplace of exponential of at. The Laplace of exponential of at. So this Laplace of exponential of at it's actually quite useful in deriving other Laplaces, right? It helps you to analyze more Laplace. That's why I love this Laplace of exponential of at. So we are going to use one more time to do this. So Laplace of exponential of at, as we know, is equal to we know that it's equal to 1 over s minus a, right? So since Laplace of 8 is equal to 1 minus s minus a. Okay, since I'm using a here, let me just change it to, let me change this to a, since I'm using a. But it doesn't matter. Okay. Now, Laplace of 8, we know this is actually equal to this. Now let's say that a is equal to ib. This I that you see here, of course, is an imaginary number. So let's assume that a is equal to ib. So if a is equal to ib, what I have is 1 over s minus a, which is now ib, right? So from the our knowledge of complex numbers, we know that a complex number, an imaginary number, shouldn't be a denominator. Hence, we should multiply by its conjugate. So if we should multiply by its conjugate, we have s plus ib divided by s plus ib. Now, if I should multiply both sides now, I have s plus ib divided by, now if I should multiply the denominator, I have s into s gives me s squared, s into ib gives me plus sib, minus ib into s gives me minus sib, and minus ib into plus ib gives me plus b squared, because I into I gives me minus 1, and multiply by this minus gives me positive. From our complex number, we should know that I is equal to the root of minus 1. So if you should multiply this, I'm going to have b squared at the denominator. Alright, so this goes with this because they are the same. So if they subtract each other, they will go. So what I have left is s plus ib divided by s squared plus b squared. Now let us separate these two. If I should separate these two, this is actually equal to s over s squared plus b squared plus ib over s squared plus b squared. So if I should separate these two, this is what I have. Now recall initially that I say the Laplace of exponential of at was equal to this. And from Euler's law, we know that exponential of I theta is equal to this. That is to say, the exponential of I at should be equal to cos at plus I sine at, right? With the same approach. Since I theta is equal to this, now the exponential of I at should give us this. And since this exponential gave us this function, we can use this to compare, right? We can use this to compare. Because from what I did here earlier, I assumed that A is equal to IB, which is to say I turned this function to the Laplace of exponential of IBT. This is what I turned this Laplace into. Okay, I turned it into this function. So that is to say, what I basically did was in this direction. This is what I basically did. Okay, was in this direction. So now let's continue. So what we have left is that since I've changed this to expression of minus 80 and it gave me this, we can compare this and this together. Okay, so I use B to get my complex number very easy. So I can write this in terms of A. This is same thing as saying in terms of A. It's same thing as saying S over S squared plus A squared plus IA over S squared plus A squared. So, okay, do you understand? So this one, you see, both are just the same thing, just A and B that I just changed. It's the same thing. Alright, because initially I wanted to solve with B. So but in the long run, I just wanted to change it to A, but they are just the same thing. Either A or B, any letter can go. So just so that these are the same. So since exponential of 80 is equal to this and the Laplace of IBT is equal to this, that means the Laplace of either cos 80 or sinh 80 is equal to the Laplace of exponential of IBT, and this is equal to x over s squared plus b squared plus ib into s squared plus b squared. So we know that by comparison, these and these are the same, right? By comparison, these and these are the same. So that is to say, because this I is I on the sign, there is no imaginary number on the cos. That means by comparison, cos BT, which is same as cos 80, which is same as cos 80 is equal to s over s squared plus b squared. So since this is for this, so if I want to write it in terms of A, I will just say s over s squared plus a squared. They are just the same thing, okay? Now sin bt in this direction now, sin bt is equal to b over s squared plus b squared, because the I has been can be eliminated from the I on this function here, right? So if I want to write it in terms of A, sin 80 will be equal to A over s squared plus b squared. So this is just the idea on how to use the Euler's theory to represent the Laplace of this function. So this is for the first part. Now for the second part, the second method I'm going to use is basically the integration by parts. Remember, so far, the definition of Laplace of a function, of any function at all, the definition of Laplace of any function at all is that function from 0 to infinity is exponential of minus st f of t. That is that function is t. So we are going to use integration by parts to also do this. So let's go with the second method of solving the Laplace of cos 80 or sin 80. So let's go to the second method on how to solve the Laplace of either cosine of 80 or sine of 80, sine of 80 as well. Alright, so I'm going to do that of sine 80, while on your convenient time, try that of cos 80. You should also arrive at the initial answer which we have arrived at before. Alright, so we know I'm going to solve for the Laplace of sine of 80. Sine of 80. So we know that the Laplace of sine of 80 is equal to the integral from 0 to infinity exponential of minus st sine of 80 dt. Now using our limit that I've said earlier on, so of course a trig function comes before an exponent. That is to say my u will be equals to the sine of 80 and my du will be equals to a cosine of 80 dt. Alright, so my dv will be equals to the exponential of minus st dt, and my v from here, I'm going to integrate both sides, will be equals to minus exponential of minus st over s. So this is what I have. So I'm going to substitute it using uv minus integral of v du. So I'm going to subtract, I'm going to use this formula to continue from it. This is IBP. I'm using integration by parts to do it, okay? Using our IBP, I'm using it to do it. Alright, so what we have left is, now this integral is now equal to what the value of our u? Sine 80. So we have sine 80 multiplied by v. What the value of our v? Minus exponential of minus st over s. Minus the integral of v. What is our v? Minus, since there is minus, let me change this to plus. Alright, so you are going to have exponential of minus st divided by s. What is the value of our du? The value of our du here is a cosine of 80 dt. So this is what I have. Remember, as I told you earlier on, anytime you get the value of your uv, always impute your limits. Always impute your limits. So now let's impute the limits. So we know that this limit now is from 0 to infinity, right? This is from 0 to infinity. So if I impute 0, if I impute infinity into the value of c, I'm not going to have 0 because the exponential of minus infinity is going to give me 0. Then if I impute the value of 0 into the exponential of minus 8, I'm going to have 1. But if I press sine of 1, I'm going to have 0 because since there is t here, sine of 0 is going to give me 0. Hence, this limit goes to 0. So what I have left is this is equal to now, what I have left is the integral of 0 to infinity exponential of minus st sine 80 dt is equals to, what I have left here is equals to the integral of 1 over s, because I can decide to bring out 1 over s outside of this function. So if I decide to bring 1 over s outside of this function, okay, I have a. If I decide to bring out a over s outside of this function, I have a over s integral of 0 to infinity. Then what I have left is exponential of minus st cos 80 dt. So this is what I have from here, right? So what I will do next is also to use integration by parts again to integrate this function. Integration by parts. So using integration by parts again, u here will be equals to cos 80 and u will be equals to minus a sine 80 dt. dv will be equal to exponential of minus SC dt, while V will give me minus exponential of minus SC divided by S. Hence, this integral now is equal to A over S into UV, that is minus cos AT exponential of minus SC over S minus VDU, right? Minus VDU. I'm using integration by parts again. Minus VDU. So V here, since it's half minus, I'll change this to plus. So exponential of minus ST over S. And what is the value of my VU? Minus A exponential of minus A sine AT dt. So this is what I'm going to have, right? So remember that A over S is multiplying the entire function. So I'm going to expand. So if I should expand, I have A over S minus A over S, okay, minus A cos AT exponential of minus ST all over S squared plus A over S into the integral of 0 to infinity exponential of minus ST over S multiplied by A sine AT dt. Alright, so this is what I have, right? So I'm going to also impute my limit from 0 to infinity. So if I should impute my limit from 0 to infinity, if I should impute my limit from 0 to infinity, what I'm going to have is, if I impute infinity into this function, so if infinity goes into exponent, and since the exponent has a negative, we are going to have 0. Minus, we are going to have 0. So what we have here is, let me do the low math. What we have here is minus A cosine of A into infinity. Remember, I told you that the values of your t is the values of this limit, right? So exponential of minus S into infinity divided by S squared minus lower limit into the upper limit, right? So the lower limit is being subtracted from the upper limit. That's why I have this minus. So minus, but since there's a minus here already, that is plus A cosine of A multiplied by 0 exponential of minus S into 0 divided by S squared, right? Plus, okay, I have a negative here. I have a negative here, so the negative comes outside. So if the negative comes outside, I'm going to have minus A squared over S squared. I have minus A squared over S squared because S into S gives me S squared. And A into A gives me A squared. Of course, there's a negative outside. So when it comes out, what I have is the integral from 0 to infinity, the exponential of minus SC sine AT dt. So this is what I'm going to have. So this type of integral is what we call I call it a recursive integral, like the integral that keeps repeating itself. Because if you see, as you can see, the original integral that we've been doing was integral from 0 to infinity of this function. And as you can see, the integral is also repeating itself in this function. So, but there's something we are going to do. But before we do that, let us break down our limits. So I know that this is going to be this one because of exponential of minus infinity. S times infinity is going to give me infinity. So exponential of minus infinity is going to give me 0. So this goes to 0. Now, on this other hand, exponential of 0 gives me 1. Cosine of 0 gives me 1. So what I have there is A over S squared. What I have there is A over S squared into A over S squared into minus now A squared over S squared into minus A squared over S squared integral of 0 to infinity exponential of minus ST sine AT dt. But remember that the original integral that was equal to this integral was this integral. That is the integral of That is the integral of 0 to infinity exponential of minus st sine at dt. Okay, recall that this was the original integral, and when we kept on integrating, we arrive at this function, right? So what we do is that since these and these are equal, since they are the same, so we are going to let I equals the integral from 0 to infinity exponential of minus st sine at dt. So we are going to do that. Alright. If you do that, it means that I is equal to, okay, so it means that I is equal to a over s squared minus a squared over s squared. Right? So this is what we are going to have. Now, if I should take this over to this other side, I have I plus a squared I over s squared is equals to a over s squared, right? So let's add the left hand side. So what we have there is s squared. We have is squared plus a squared I, right, is equals to a over s squared. So when we factor out I on the numerator, we have I into s squared plus a squared over s squared is equals to a over s squared. Alright, so but what I need to get is the value of my I. So if I set to multiply both sides by, I'll multiply both sides by s squared over s squared plus a squared. So I'm going to multiply by the inverse of this function to eliminate all my i's. Right? So if I should do that now, what I'm going to have is, if s squared multiplies s squared will go. If s squared plus a squared multiply a squared, so that means on my left hand side now, I only have I, right? Okay, is equals to, now if s squared multiplies s squared goes, but what will remain is a over s squared plus a squared, right? So this is the value of our I, but recall that I is equal to, recall that I is equal to the integral of 0 to infinity of exponential of minus st sine at dt, which of course was equal to the Laplace of sine 80. Hence, the Laplace of sine 80 is equals to a divided by s squared plus a squared. So that is the value of sine 80. So this is basically the same thing that we did in the first method. The only difference was that we didn't use the definition of the Laplace, we only used the Euler's law to do it. But in this situation, in this second method, I used the direct approach of the Laplace of sine 80. So, in your respective reading, your study as well, also try to use this method to do the Laplace of cosine of 80. It's just the same approach, just using IDP, integration by parts, maybe 2 or 3 times, then you arrive at your answer. So before we close on this one, so that is to say, if you are asked the Laplace of sine 3t, the Laplace of sine 3t will give you 3 into s squared plus 9. If they ask you to do the Laplace of maybe sine 5t, so sine 5t will give us 3, now 5 into s squared plus 25. So this is how to analyze the Laplace of sine 80 and cosine of 80. Now we are left with one more Laplace to do, and that is the Laplace of a hyperbolic function, of a hyperbolic function, the cosh and the sinh. So we are going to do that, and then that will be all you need to know about the f of t's of Laplace. Then you can go ahead to solve as many Laplaces as you want, and then at the long run, we are going to do, maybe in our next video, we are going to do, show you how to solve the Laplace, how to solve differential equations using Laplace transforms. But mind you, this Laplace transform can also be used to solve simultaneous equation. It can be used to solve many sets of equations. It's a very, very useful function in mathematics as a whole. So let's go through the last Laplace and see how it goes. That's the Laplace of a hyperbolic function. So as I was saying, so we are going to go through the last Laplace, which is the Laplace of a hyperbolic function. Okay. So in this situation, let's assume that f of t is equals to cosh at. Okay. Let's assume that f of t is equals to cosh at. So we are going to do. Remember, these also have probably about 2 or 3 methods, but I'm just going to use one method to do this. So the other method, which is the usual definition of Laplace of a function, probably on your leisure you also try it. It's still very simple. But this, I feel, this is basic. The method I'm going to use now is very easy and very basic for anyone to comprehend. Right. So the Laplace of this function is done in this way. We know that we are going to apply our knowledge of the Laplace of exponential of at, right? So as I told you, that Laplace of exponential of at is one of the most crucial Laplace because it helps us to analyze more Laplaces and helps us to decipher as many Laplace as we want. So we know a little recall that the Laplace of exponential of at is equal to 1 over s minus a, right? So this is the Laplace of at. So, but from the definition of this hyperbolic function, cosh at, its definition is cosh at is equals to 1 over 2 into exponential of at plus exponential of minus at. So this is the definition of the cosh of a function. This is its definition. So you can say this is equal to exponential of at plus exponential of minus at divided by 2. Okay? This is the definition of the cosh of a function. So using that, we already know the Laplace of exponential of at. We already know the Laplace of exponential of minus at because they are just basically the same thing. So this is now equal to 1 over 2. The Laplace of this cosh at now is equal to 1 over 2. We know that the Laplace of exponential of okay, let's go through this way. The Laplace of cosh at is equals to the Laplace of 1 over 2 of exponential of at plus exponential of minus at, right? So let's go through it like this first. Alright, so one of the rules of Laplace as well, as I told you earlier, is that just like an integral, a Laplace, a constant can come out of the Laplace, right? So if the constant comes out of the Laplace, that is if 1 over 2 comes out of this Laplace, this is saying that saying 1 over 2, the Laplace of exponential of at plus the Laplace of exponential of minus at. Alright, so if you want, you can try to expand, you can try to expand this Laplace. If you want, you can try to go through this way. Right? So let's assume that I want to expand this. So this is saying, this simply means 1 over 2 into the Laplace of exponential of at plus the Laplace of exponential of minus at. Right? So this and this are basically the same. Now if I should do the Laplace of exponential of at, what I have is 1 over 2. Well, I know that the Laplace of exponential of at gives me 1 over s minus a. And the exponential of minus at will give me 1 over s plus a, right? So if I should add the what I have inside my bracket, I have 1 over 2 into, I have s minus a and s minus s plus a, right? So since I have this now, then I have s plus a plus I have s minus a. So now s, okay, a can go, so I have s remaining. So what I have left is 1 over 2 into 2x divided by, now at the denominator, as you can see, this is the difference of 2 squares. So I can write s squared minus a squared. Alright, so 2 can cancel 2. So what I have is s over s squared minus a squared. So this is the value of the Laplace of cos 80. Okay, Laplace of cos 80. So that is the value of the Laplace of cos 80. So before we do an example of this Laplace of cos 80, let's quickly do the Laplace of sinh 80. So let's assume that f of t, is equals to sinh 80. Let's assume that f of t is equals to sinh 80. So how can we analyze the Laplace of this sinh? Right? So I want you to know that sinh 80 is actually equal to 1 over 2 into the exponent of 80 minus the exponent of minus 80. Okay, this is the definition. So the difference between the cos and the sinh is just the signs on them. Right? So that is to say, the Laplace of sinh 80, the Laplace of sinh 80 is equal to the Laplace 1 over 2 of exponential of 80 minus exponential of minus 80. So this is what we have. And now this is equal to, as usual, just like we did here, 1 over 2 into the Laplace of exponential of 80 is 1 over s minus a, and the exponential Laplace of exponential of minus 80 is minus 1 over s plus a. So this is what we have. Alright, so I'm just going to extend it over here. So let's subtract what we have in the bracket. So if you subtract what we have in the bracket, we are going to have 1 over 2 into s minus a and s plus a, right? So what I have is s plus a minus s minus a. So this is what I have. So I have 1 over 2. I have 1 over 2 into s plus a minus s plus a divided by x squared minus a squared, because this is the difference of 2 squares, right? So s can cancel x. What I'm left with is only a. So I have 1 over 2 into 2a divided by s squared minus a squared. So of course 2 cancels 2, right? So what I have left is a over s squared minus a squared. So this is the value of the Laplace of sinh 80. This is the value of Laplace of sinh 80. Alright, so we are going to just do 1 or 2 examples of them and we'll see how it goes. So if we're asked to find the Laplace, of sinh 2t, that means we know that sinh is already equal to a over s squared minus a squared, and here a is equal to 2. That means 2 over s squared minus 4, right? So that is the value of sinh 80. What if we are asked to find the Laplace of cos 80? cos 2t rather. So what if we ask to find the Laplace of cos 2t? So cos has s at the numerator, right? So since it has s at the numerator, it's going to give us s over s squared minus 4. So that's the value of the cos. Now let's run through one more example. So let's say we ask to find the Laplace of sinh t. So looking at the Laplace of sinh t, you can see that the value of a here is 1, right? So the value of a is 1, you have 1 over s squared minus 1. And if they ask to find the Laplace of cos t, it's going to give us s into s squared minus 1. We're going to have s into s squared minus 1. So this is all you have to know about the f of t's of all the Laplaces. I've explained them. So if you have any question as you are going through the video, just drop the question in the comment section. I will answer it. Right? So in your leisure time, just pick any method of your choice and go and do it. You might decide not to use this approach to solve this particular Laplace. If you want, another method, which I'm not going to do now, is using integration by parts again to solve the Laplace. Knowing, having in mind that the Laplace of cos 80, the Laplace of cos 80 is equals to integral from 0 to infinity exponential of minus st cos 80t. Right? But if I should use this method, it's actually going to be very long. That's why I decided to use a shorter output by employing my knowledge of the hyperbolic functions. So I hope this video was useful and helpful. Please remember to like, subscribe, and share. Once more, this is Infinity YouTube channel. Please remember to like, subscribe, and share. Thank you.